Periodic and aperiodic signals. Consider a signal x1 of t which is defined from 0 to t0 as shown in this figure. T0 is signal width in time domain. Before 0 and after t0 the signal value is defined as 0. To understand this periodic signals, consider the signal that is defined for a duration t0 and shift the signal to right side as well as left side by integer multiples of t0. That is by t0, 2t0, 3t0, etc. Move the signal to right side by a value t0. That portion is taken from t0 to 2t0. Then move the signal to right side by a value 2t0. That portion is taken from 2t0 to 3t0. Similarly, move the signal to left side also. Shift the signal to left side by a value t0. That portion is defined from 0 to minus t0. Then move the signal to left side by a value 2t0. That portion is taken from minus t0 to minus 2t0. Let's define each portion of t0 as one replica and take infinite replicas ranging from minus infinity to plus infinity. Such a signal is taken as x of t. So, the signal x of t contains x1 of t and its shifted versions by integer multiples of t0. Take x1 of t as first replica, then x1 of t minus capital T0. That is the right shifted version of x1 of t by a value capital T0. Next replica x1 of t minus 2t0. Similarly, at left hand side, x1 of t plus capital T0. That is left shifted version of x1 of t by a value t0. This is another replica which is given by x1 of t plus 2t0. So like this, we can take every integer multiple of t0 and the signal can be defined from minus infinity to plus infinity. So let's define x of t as a linear combination of x1 of t plus x1 of t minus t0 plus x1 of t minus 2t0 so on up to plus infinity. Similarly, at negative time, for negative time axis, x1 of t plus t0 plus x1 of t plus 2t0 and so on up to minus infinity. So the signal x of t can be represented as summation k equal to minus infinity to plus infinity x1 of t minus kt0, where k is an integer, that is k equal to plus or minus 1 plus or minus 2 plus or minus 3 as well as k equal to 0 also. Such a signal x of t is called periodic signal. Ideally, a periodic signal is defined from minus infinity to plus infinity, so such as a linear combination of infinite replicas. So far in this discussion, to explain the periodic signal x of t, we have taken help from a reference signal x1 of t. How to define the periodic signal in its own way? So there should not be any reference signal like x1 of t. Such a periodic signal x of t can be shown now like this. This signal is defined from minus infinity to plus infinity with infinite periodic repetitions or extensions, which we usually call replicas. Each replica is of width or duration capital T0. Now, to define the signal x of t, shift this signal to right side, shift this signal x of t to right side by a value capital T0, so that the replica from minus 2t0 to minus t0 will be moved to minus t0 to 0. The replica at minus t0 to 0 will be moved to 0 to t0. 0 to t0 will be shifted to t0 to 2t0. Like this, the signal will be moved to right side. As a whole, by considering the signal from minus infinity to plus infinity, there is no change in the signal by a shift capital T0. That is, x of t is equal to x of t minus t0. Similarly, move the signal x of t to left side by a value t0. There is no change in the signal. Shift the signal to right side or left side by values 2t0, 3t0, 4t0, etc. There will not be any change in the signal x of t. That can be expressed as x of t is equal to x of t plus or minus kt0. We know k is an integer. What is the meaning of this expression? Consider the signal x of t, shift that signal either to right side or left side by a value t naught or its integer multiple. The shift by a value t naught does not bring any change in the parent signal. That is, the shifted signal is same as the parent signal. In general, a periodic signal can be defined as follows. If a signal x of t is shifted either to left side or right side by a value t naught or its integer multiple is giving the same signal, then it is called periodic signal. Here, t naught, 2t naught, 3t naught, 4t naught, etc. are called periods of the signal x of t. So, periodic signal can contain infinite periods, but the signal can have only one fundamental period. What is fundamental period? The minimum value with which the signal repeats is called fundamental period. The minimum value with which signal repeats is called fundamental period. Capital T naught is the fundamental period which we have taken here to define the signal x of t. The reciprocal of fundamental period is called fundamental frequency, that is given by f naught is equal to 1 by t naught or omega naught equal to 2 pi by t naught. This fundamental period or fundamental frequency are very important to identify or to characterize periodic signal. So, periodic signals are always characterized with fundamental period or fundamental frequency. The way how you will be identified with your name, in a similar fashion, periodic signals will be identified with fundamental period or fundamental frequency. A signal which does not satisfy this condition is called a periodic signal. Such a signal expression can be given as x of t not equal to x of t plus or minus kt naught. Examples for such an aperiodic signal is shown as follows. First, this is a finite duration aperiodic signal. The signal is defined from minus tau to plus tau. Similarly, there is another aperiodic signal which can be defined like this. This is an infinite duration aperiodic signal. The signal is defined from minus infinity to plus infinity in an aperiodic manner. What is the fundamental period of an aperiodic signal? It can be taken as infinity. The fundamental period of an aperiodic signal is taken as infinity. That is, in the signals x2 of t and x3 of t, the next cycle occurs at infinity, which means it will never occur. This is about periodic and aperiodic signals. Summation of periodic signals. We know periodic signals are characterized with their fundamental period. Consider four periodic signals x1 of t, x2 of t, x3 of t and x4 of t with their fundamental periods t1, t2, t3 and t4 respectively. And define a signal x of t which is a summation of these four periodic signals. X of t is equal to x1 of t plus x2 of t plus x3 of t plus x4 of t. The signal x of t is a summation of four periodic signals. What about its periodicity? Is this signal x of t always periodic? The answer is no. Then, when the signal x of t will be periodic? If an LCM of the fundamental periods involved in the summation exists, then the resultant will be periodic. That is, in this example, x of t will be periodic if an LCM exists between t1, t2, t3 and t4. So, this can be summarized as, if an LCM of fundamental periods of the signals that are involved in the summation exists, then the resultant signal will be periodic. If x of t is periodic with fundamental period t naught, then the t naught will be the LCM of t1, t2, t3 and t4. There is a step-by-step procedure to determine the fundamental period of summation of periodic signals. As a first step in this procedure, form the ratios by taking any one signal fundamental period in the numerator and taking the remaining signals fundamental periods in the denominator. For this example, obtain the ratios t1 by t2, t1 by t3 and t1 by t4. Among these ratios, if any one ratio is irrational, any one or more than one ratios are irrational, then such a resultant signal x of t will be aperiodic. If all the ratios are rational, then the resultant will be periodic. If x of t is periodic, then its fundamental period is to be calculated. To determine that fundamental period t naught, eliminate the greatest common factor in every ratio and get the LCM of the denominators and denote this LCM as capital P. This capital P multiplied with the numerator that we have taken in our earlier ratios gives the fundamental period t naught. In this way, periodicity of the summation of periodic signals can be determined. Solid example. Three signals x1 of t, x2 of t and x3 of t are periodic with fundamental periods t1, t2 and t3 respectively. A signal x of t is defined as x of t is equal to x1 of t plus x2 of t plus x3 of t. If x of t is periodic, then t naught is its fundamental period. Fundamental periods t1, t2 and t3 are given as follows. In first case, 2, 7.5 root 3. In second case, pi by 4, pi by 8, pi by 12. Third case, 2, pi by 4, 9. Fourth case, 1.08, 3.6, 2.025. First, comment on periodicity of x of t in 4 cases. And next, if the signal is periodic, determine its fundamental period. In first case, the fundamental periods of x1, x2 and x3 are given as t1 equal to 2, t2 is equal to 7.5 and t3 is equal to root 3. So according to the procedure that we have studied, get the ratios of fundamental periods by considering one fixed fundamental period in the numerator. Consider t1 in the numerator and obtain t1 by t2, that is equal to 2 by 7.5. Next, obtain t1 by t3, that is equal to 2 by root 3. 2 by 7.5 is equal to 20 by 75. This ratio t1 by t2 is rational. If the numerator and denominator both are integer values, then such a ratio is rational. But in the second ratio, 2 by root 3 is an irrational number. Square root of prime numbers are irrational. Root 3, root 5, root 7, root 11, root 13, etc. are irrational. So the ratio t1 by t3 is irrational because of the presence of root 3. Therefore, the signal x of t is aperiodic. Next, in the second case, the fundamental periods are defined as t1 is equal to pi by 4, t2 is equal to pi by 8, t3 is equal to pi by 12. Again, get the ratios by considering any one fundamental period in numerator. Intentionally, I am considering t2 in the numerator. So get the ratios t2 by t1 and t2 by t3. t2 by t1 is equal to pi by 8 divided by pi by 4. That I am taking as pi by 8 into 4 by pi. So this is equal to 1 by 2. Next, t2 by t3 is equal to pi by 8 divided by pi by 12. That can be written as pi by 8 into 12 by pi. That is equal to 3 by 2. If we observe the ratios, both are rational. Therefore, the signal x of t is periodic in nature. If the signal is periodic, then immediately we have to calculate its fundamental period. In the obtained ratios, eliminate the GCD. But here, in both the ratios, there is no GCD. Then get the LCM of the denominators. Both the denominators are 2, so that LCM of 2 comma 2, that is equal to 2. Define this value as P. The fundamental period T naught is defined as fundamental period in the numerator of the ratios multiplied with P. That value is pi by 8 into 2. Therefore, fundamental period T naught is equal to pi by 4. Third case, the fundamental periods are defined as T1 is equal to 2, T2 is equal to pi by 4 and T3 is equal to 9. Again get the ratios. Here in this case I am taking T3 in the numerator. So obtain the ratios T3 by T1 and T3 by T2. T3 by T1 is equal to 9 by 2, which is rational. T3 by T2 is equal to 9 by pi by 4, that is equal to 36 by pi. A very important point here is pi is an irrational number. pi should not be taken as 22 by 7. Pi is an irrational number. Therefore, the ratio T3 by T2 is irrational, and the signal x of t for the given fundamental periods is aperiodic. Next, in the fourth case, T1 is equal to 1.08, T2 is equal to 3.6, and T3 is equal to 2.025. Get the ratios T1 by T2 and T1 by T3. The ratio T1 by T2 is equal to 1.08 divided by 3.6. That can be written as 108 by 360. So that this ratio is irrational. T1 by T3 is equal to 1.08 divided by 2.025. So this value is this ratio is equal to 1080 divided by 2025. This ratio is also rational. As both the ratios are rational in nature, the signal x of t is periodic. Then the fundamental period is to be calculated. To get that, eliminate the GCD in both the ratios. In the first ratio, 36 can be eliminated and it can be written as 3 by 10. In the second ratio, 135 is the GCD and the ratio can be simplified to 8 by 15. Now, according to the procedure, get the LCM of denominators. That is, LCM of 10, 15 is equal to 30 is defined as the value of P. The fundamental period T0 is equal to the numerator fundamental period we have taken T1 here multiplied with the value of P, that is equal to 1.08 into 30. Therefore, T0 is equal to 32.4 is the fundamental period. Here in this example, for the signals x1, x2 and x3, the given fundamental periods in case 1 and case 3 are giving an aperiodic signal because of the irrational behavior of one ratio. Whereas in second case and fourth case, the signal x of t is periodic and their respective fundamental periods are calculated.